It's all from the book. Which book? The one here. So everything is there. Everything is there. Yeah. That was mentioned also it's the same question.
Good morning. Today, before I jump to the lectures, I want to discuss a bit about the coursework. So if you go to the Moodle page, we have all important here. Go to the coursework submission tab. I have put 3 tabs here. The third one, this one, is for, it's not for now, it's for when you want to submit your final work, okay? It will be open on, I think, 19th of December and will be open until 6th of January. And the 6th of January is really the latest date I can imagine for the courseworks. However, you're more than welcome if you submit your coursework in December and don't want to be bothered by it during the Christmas holiday. But anyway, I will leave it open until 6th of January. Those people will have some finish it or time. So, but please don't be late and put it in your calendar, and I won't accept any late submission. These 2 are for your courseworks. Part 1, your coursework part 1, because you will have another one in the next semester. Something similar in content, I mean, something in time scheduling similar to this one. And there is a coursework brief. I will open it, and students parameters. If you open the student parameters, it's an Excel file which lists all the students here. Okay. This is something that you can find yourself in it. And when, if name, surname, ID number, or email is not correct, tell me, because I've gotten this from the Moodle. And if anything is wrong here, we need to inform the administration about it. So everyone will find a name and a line for itself. And here are the parameters you will need. L1, L2, E, new, A, I, and P. So this I means that this is 60,000, sorry, 6 divided by 10,000 in terms of M4, okay? It means that this division by 10,000 will be applied for all of them, okay? That's why I haven't repeated here. So let's put here this one in the second window here. And I will go to take a look at the coursework brief to see where we will use these parameters into our problem. So this is your coursework. It's not really different from what we have talked during the lectures. And before I go through the coursework content, I want to remind you all. Now we're talking today, we are living in the week number 8 of the semester, which means week number 6 of the lectures, because lectures started from week 3. right? And we will have 12 lectures during the first semester. Today, we are living with a 6-lecture week. So it means that we are really and absolutely in the middle of the term 1. And this is a very important milestone for any module, including this one. And if anybody haven't spent enough time for studying the lectures, it's maybe the latest time that you can just recover yourself and get in the line. Otherwise, if you give more time and just approach the end of the semester, you'll be very late to recover yourself. And also, having a lecture, you are year 3, so I assume that you all know these things, but attending to the lecture is not enough for learning the module and passing it. So you really need to spend more time out of the lecture hours for studying the lectures, doing revision, doing the tutorials, working with ETABS, and studying the books. So you really need to spend, let's say, 4 hours per module every week, 5 hours, 3 hours, depends on the week. But if you, I don't know, but if you really just attend the lecture and do not do anything until the next week's lecture, it would make some problems. And I told you before this that after a while you will think that you have lost during the lectures. So really, if you have lost now, it's the time to get back in line. And as you know, we are 24 in the class based on this list here, and now we are 10. So 15 or 14 are absent. They don't care probably. And I cannot do anything really for anybody who doesn't care. If you don't care about the module and you don't want to spend time for study, what can I do? The thing that I can do is just to deliver the lectures and remind you that this is the time to do this, to do that, to get involved in this, to get involved in that. Otherwise, if you insist, I mean anybody, if you insist that you don't want to get involved, get engaged in the activities, what can I do? So, but as far as I know, the only way to pass this module is to get engaged, do the exercises, do the coursework, do the activities, study the lectures to pass this course. I myself don't know any other way to be succeeded in this module. You know, you can follow that route, but I know this path to pass this exam, this module. So this is really the last call for getting back to the module, because we're really in the middle of the way for the first semester. Yeah.
How much is the word limit or the page limit for this assignment?
I think I haven't put any limits for any module. For all of my modules, the report is free. You can put, I will talk about it. I've put it here, important notice. First of all, let me first explain this part, and then I will get back to this part, which is your answer. Let's take a look at the structure. The structure is a determinative structure, really easy to solve manually. You can really find the support reaction, everything in 5 minutes here. But you're dealing with this single structure. It's a 2 segmented beams, A, B, C, simple support, a roller support, L1 and L2 and P. So L1 and L2 are here, L1, L2 and P. Everyone has an individual set of parameters. So L1 and L2 for you equipment, for you is this. So everyone will take appropriate values from the Excel file, right? So although the shape is the same, but the geometry is different for any individual. You need to do 8 steps in your calculation, in your report. And I need to see these A1 to A8 in your submission. You should write A1, manually find the support actions and draw internal bending moment there. Okay. You can put some Word file, you can scan your handwriting, you can do whatever and put it there and go to the A2. That's your report. Okay? And obviously for A1, it should be handwritten. You should write it, scan it.
Can we type it in?
Yes, you can type. But it's a hassle because you need to draw some shear and bending. But if you do that, yeah, that's beautiful. You can do whatever you want, but I need to go in this part first. But the important thing is this one. The submitted report has no limitation as long as the provided information and calculations have merit from an engineering point of view. Please, please, please do not add mass production data into your report, such as ETABS, analysis, outputs, etc. If you go, I will go through the ETABS steps, for example. And when you model any structure with ETABS, you can generate thousands of pages output of ETABS. If you put those kind of stuff in your report, you will fail in your coursework. I've clearly stated here. Whatever you put in your report should make sense from an engineering point of view. You should say, okay, I found this moment here, that deformation here, because of this, because of that, that's totally fine. But if you put, okay, I've put 20 pages output of ETABS, like tables, 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 that doesn't merit at all. So I assume that this report can be something like 10, 15 pages with important outputs of your calculations. Otherwise, submitting 100 pages is possible, but doesn't merit. So there is no limit because it's the real world. Why I don't put a limit? Because it's the real world. When you go to the outside of university to work, there is no teacher on yourself to say, okay, you need to follow this instruction for your report up to 5 pages with this font, with that font. There are some regulations, but there is a stakeholder which gives you some project and you need to prepare the report, and it should be engineering report. It should make sense from engineering point of view. So you can put some tables, some figures, some calculations based on your engineering judgment, but there is really not any limit for that. And as a principle of engineering, you should squeeze your report, you should squeeze your drawings, engineering drawings, you should squeeze your calculation as much as possible to give the best information to the stakeholder in the least space you can do that. It's also true for the drawings. When you work with AutoCAD for draw some engineering engineering drawings, you need to give the most information you can to the stakeholder, to the engineering who is gonna construct this structure with minimum lines, minimum things you put in your map. You should not repeat everything. You should not repeat something from this one to that one, to that one, to that one. It's annoying when you are using a map and you see repetition everywhere. It's also true in your report. So you should learn how to write reports and how to write it in minimum pages with maximum information. This is the idea that you need to think of. Minimum pages, maximum information, delivery information. A1 is really 10 minutes to do, or 15, or half an hour, whatever you want. This is really just to start the problem. A2, find the translational and rotational deformation at node C by using Castigliano's theorem. Here. How much C comes down and how much C rotates. This is really the same as many things that we followed in this module in the recent lectures. And it's really, again, easy to do, maybe 1 hour, 1.5 hours, something like that. Okay? Is it clear, A2? A3, find the same things, translational and rotational deformation at node C by using the virtual work method. Virtual work method is some method similar to Castigliano. Today we are going to teach that. Okay? That's another method of energy, like Castigliano. Okay? And compare the results with step A2. So I anticipate, and you should anticipate, that what you have obtained from A2 and A3 would be more or less the same because you're solving one problem. A4, model the beam by using ETABS and compare the result with the steps A2 and A3. So far you have 2 offline videos in the Moodle, how to use ETABS, right? And if you watch them, I assume that you are really can do a 4-step. However, on 25th of November, we will have IT labs for this module, and it's in Nelson, okay? Please, we have probably 2 weeks until then, 2 or 3, I don't know, 3 weeks. Anyway, today is 4th, so 21 days, 3 weeks, yes. We have 3 weeks left. Please try to do a 4-step until that time, and we will spend that session in the lab, and I will check on you each one by each one to see how you deal with a 4-step, okay? We will leave a 4-step for 25th of November and not leave it for there. Just try to build up your draft model and we will try to solve the problems in that day.
On a personal license.
Unfortunately, it's not possible. You need to just use Nelson computers. You can go there before any time that there is no class activity, you can go there and ask. Anytime you can go there and get a computer and work, okay? Try to prepare your model before that day, and that day we will spend the whole class in there and solve your problems regarding the ETABS, okay?
Does it work on the main campus approach?
Greenwich, yes. See, I just show you, no, here. Where is, yeah. Here is your Moodle, isn't it? This is your Moodle, or the module. News and announcements, okay? ETABS is also available in 2nd and 3rd floor of Stockwell Street Library for students. If you have received this email, please read your emails when you get one, at least from me, okay? You have received this email on 20th October, a couple of weeks ago. So it says that it works in Nelson here, OC means Nelson, and these are the numbers of the rooms. These are 3 rooms in Nelson, 2 rooms in Hawk, but I'm not sure if Hawk is open or not because of leakage problems. This is in Greenwich site. If you go to Greenwich D236 and GM446, these are 2 rooms that you can get there and get emails. Okay? So this you have this email in your inbox from 20th of October. Otherwise, any of these work for you to go there and get some experience before 25th, and for 25th we go in Nelson and try to solve any potential problem. And the objective of mine is to force you to learn ETABS, although you don't want to learn it. Okay? It's the point. You have 3 weeks to build up. Really building up this model needs 15 minutes or half an hour, not more. Like I did for that truss structure or that cantilever beam, and you can find the video. It's less than half an hour.
We do use ETABS in an engineering profession.
Too much. It's a very well-known software worldwide and very capable of doing different kinds of analysis engineering's need. It's a very good software. And it's really an opportunity to learn this in this module. So, A5 says find the same thing, translation and rotational deformation of node C by using the finite difference method. What is this finite difference method? Do you remember the name? Have we taught it, or we are gonna teach it? Yeah. Do you remember that Excel with different segments? That's finite difference, okay? You need to follow the same steps there. Okay? You need to follow the same steps we did for finite difference a few weeks ago with that Excel file. Whatever you do for your coursework, you need to accompany with the files. If you're using Excel for A5, just put Excel in your submission. Okay, I need to see what you have. A6 says find.
Can you attach more than one submission in the? There's normally let's say, for example, you're saying you have to attach an Excel files if you do the calculation. Is it possible to attach this?
Yes, it is. Otherwise, if you saw that you are limited to one file, make a zip file of all of your files and attach the zip file. I will unzip. Okay, that's the simplest way. A6 says find the translational and rotational deformation again at C by using direct stiffness method and compare the results with step A4. Direct stiffness method is something that we are going to teach in the next lectures. We are in the halfway. The next halfway, we will teach virtual method, something today and next week. Then we will go for, it's called matrix analysis. We'll deal with different matrices. And we will spend a couple of weeks for matrix analysis. And the stiffness method is related to that one. You will see, they are the same. And solving this with matrix analysis needs 1 or 2 hours. A7 says, okay, A7 is something interesting. And A8, the last one, is discussion about the results obtained in A7. This is something interesting that I need to elaborate a little. So, yeah, in the Excel file, you had cross-section area in terms of square meter for everyone, okay? Here. Good morning.
Yeah.
Mr. Fari.
Nothing? All right. Right in time because we're going to illustrate about the most important step in the coursework.
Oh, lovely. Yeah.
So far, until A6, you had these data and you had a column, a value for A, cross-section area. That's fine, okay? But in A7, forget about this A, and we will deal like this. It says, change the beam's cross-section to be a rectangular section. Let me just put it here. And we have this here. It says that, suppose that our section is a rectangular section with, this is B equal to 40 centimeter, and this is height, H, which is H. Okay? Consider H varies between 40 to 200 centimeter. It's 40, you can assume whatever you want. You can go 10 by 10, 20 by 20, whatever. 50, 60, go to 200. And to be honest, you can change this part if you wish. You can go from 30 to 300. You can go from 40 to 500, whatever you want. I want to cover a range for H, a wide range for H, okay? Have different values. Otherwise, the numbers are not very strict. But you should cover a range for that. So I've written there, you're allowed to consider other values for B or H, but you need to cover a reasonable range for the H over B variable. And what we want in this step is draw the ratio of shear deformation to the total deformation versus H over B for the translational and rotational deformation at node C. What does it mean? It means that I want some graph like this. The x-axis is H over B. You have assumed different values for H, so you have different values for H over B. For example, if you take one case, this is 30 centimeter, 40 centimeter, and this is 80 centimeter. B, this is H. Okay, this is one of those cases. We have different cases, 40, 140, 120, something. This is one of these cases. But this case, you have A, I, something else. E, G. If you use Castigliano theorem, for example, you will be able to calculate YC or theta C, like in step A, 2, 3, what was it? Okay, when you go and calculate it, at the final, you will have really two terms. One term has EI and one term has GA, right? And you can replace EI and I and get the final value. But this is the contribution of bending moment. And this is the contribution of shear forces, right? We did this in the last lectures here. We have two terms. You can do this with virtual work as well. You can do this with matrix analysis as well, you will see. Anyway, you will have two terms, and you saw in the past lectures that this term is really smaller than this term in many cases. That means that the bending moment is the most important part, right? I want to see in A7, and this is the step of your coursework, I want to see when and how this term will get more importance. So I want to see if there are some cases that the shear force contribution to the total deformation gets more important. So I've designed this example to see how this works and if there are some cases or not. So what can I do? For this case, 40 by 80, I will go use Castigliano's theorem or whatever, virtual work, and come up with YC and theta C. For example, for YC, I will say that this is the shear for YC, and this is, let's name them whatever you want. This is the bending for YC, and this is the total for YC. We have a total deformation for YC, which consists of two parts, bending and shear, right? See here, draw the ratio of shear deformation to the total deformation. I mean, draw. The shear deformation means this one, to the total deformation means this one. This term divided by this. If you like, you can multiply it by 100 to get a percent. For example, this is more beautiful. This will be in terms of percent. How much percent is the contribution of shear force to the total deformation? Right? And this is in the case of YC, you can, so for this one, which you have 40 by 80, you will get 1 point here. If you change H to some other parameters, you will get another point. You will get another point. For any assumption of H, you will get 1 point. In how many H you have assumed, the same numbers of points you will get to connect together and draw a curve. I don't give you any advice, but you will have some curve here. I don't want to say what shape you will get. You should do it to see what you will get. You will get it for YC, you will get it for theta C, and if you like, you can do the same thing for the ratio of this one over total. This, if you divide this part to the total, you will get the contribution of bending moment to the total. That would be nice as well. And when you get this graph, you can discuss about the thing that I just said before, how this is getting important if you're looking at the shear deformation contribution, shear force contribution to the deformation, right? And you can look intuitively at your graph and say, okay, from this point, it seems that this is getting more important. And from this point, I'm looking for some point or some conclusion that you say, from this point, I cannot neglect the shear deformation. And I need to take that into consideration. So I'm looking for that point. This is what you need to do in A8 section. In A8, you need to discuss. You need to discuss where it is important to not to neglect shear force contribution to the final deformation. It means that we are, in those cases, we are not allowed to follow the methods like integration methods that only consider the bending moments. We need to go for energy-based methods like virtual work or Castigliano. Any question? And for the important notices here, first of all, whatever you have done with ETABS, Excel, or whatever, you need to attach them to your coursework. And I believe I put the submission tab free to be able to upload more than one file. But if you couldn't, just make a zip file of all of them and submit one file.
Are you allowed to use MATLAB, for instance, like, for example,
Which part?
in the stiffness, character stiffness?
Yes, you are. Yes, you are. And if you use MATLAB, just put the M file there. If you use it, yeah, it's totally fine. The second one, I say, for those who recently joined us, really not to add mass production outputs of ETABS into your report, like 10, 20 pages output of ETABS. It's not useful for your coursework, and really avoid that. And the last one, and very important one, your report must be original. You may scan your hand calculations, whatever you want, you can put in your report. And the student have to add the appropriate references to the report. So if you use something, just reference to that. In your case here, you don't have really too many references. It's more makes sense in the other modules, like design module, just to refer to the codes, etc., regulations. But for you, I assume you can just refer to the Castigliano theorem or virtual work, just to a book or two. It's okay for you, but the originality of your report should be a very important point. Please just include your work in your file that you're going to submit. Okay?
Yeah, let's say if you're talking about Castigliano's theorem, do you need to explain what it is or just show the?
No, you just use it. Those things are already in the book. Nobody's interested with that. You need to, as we do for the example, you need just to start to solve your problem. I'll explain that. I put this force here because of that. I'm going to derivate this one for that one because of those. Okay? First of all, the coursework is not difficult. Second of all, the coursework is exactly in line with what we have taught during the lectures. Third of all, we need to wait for virtual work and direct stiffness method for some of the steps. Okay, that's what we will cover during the second half of the semester, third semester. That's fine. And also, for those just recently joined the class, we said that prepare yourself for the A4, which is simulating this structure into the ETABS. And you, first of all, you have 2 offline videos in the Moodle. You can get help of them to prepare yours. And also, on the 25th of this month, November, we are going to Nelson Lab. Our session will be there, and we will dedicate that session for A4 for your coursework. So until then, try to do A4 step. And if you get any problem, we will go there and discuss about solving the problem. Okay? If you didn't get any problem, bring your results there and we will take a look at them. I will go individually from one to another that way to see what you have done for A4 step. Okay? And what else? Okay, if you have finished some of other parts until 25th, you can take a look at them as well. Anyway, any question? Everything is clear? Good. If everything is clear, we can jump to the lectures again. And to just give you a clear overview of the next half of the first semester, we have covered some methods. The last one was Castigliano. Before that was integration method and stuff like that. As you see, we are progressing through the different methods. How? The integration method was able to only consider bending moment. Remember, phi difference was the same. They were dealing with the problem only by considering the bending moment into the problem, and they couldn't understand shear deformation or axial deformation. We stepped forward for Castigliano, which is a kind of energy-based method. The integration was not energy-based. It was based on some other theories. So Castigliano was based on energy, and you can imagine, always in different disciplines of engineering, always energy-based approaches are superior. Because energy principle is something very important in physics. So those methodologies that are built upon an energy scheme is usually superior rather than the other approaches. Castigliano was the first one. Virtual work is the second. Virtual work is the second one. These two approaches are both very strong approaches, very good approaches. However, you will see that in some cases, virtual work is superior rather than the Castigliano. I mean, although both approaches are good, but in some cases, the Castigliano will face some difficulties to solve the problem, or ambiguities rather than difficulty. But virtual work is not. Virtual work is really the best method among all the force-based methods. Why I say force-based method? Because all of these methods that we have covered so far, which the last one will be virtual work, all of them are based on force. We deal with forces, right? Among the force-based methods, the virtual work is the best one, which can solve really any kind of problem. Castigliano is good for probably 95% of the problem. In 5%, it faces some difficulties. And the previous approaches are, you know, they just take bending moment into consideration, right? All of these force methods still are somehow influenced by the deformation-based methods or stiffness-based methods, which is the next one, which is, I showed you some of the steps in your coursework are about direct stiffness method. The direct stiffness method is something, or matrix analysis, is something that is based on deformation-based approaches. And always deformation-based approaches are superior than the force-based approaches. This is the overview that what we are covering until the first semester, right? So the virtual work, we are going to speak about it today and the next week, is really something very good among the force-based approaches. However, the deformation-based approaches, which is the next one, is always superior than the force-based approaches. So, although the demonstration of virtual work is really very simple, but again, I skip it because I don't want to mix you up with some demonstration. I want to give you the main idea how to solve the problem. Otherwise, if you learn that one, if you come back, you can easily figure out how we can demonstrate the approach. And for the virtual work, we always have two structures. Whatever you are aiming at solving, like this. For example, you want to solve this. This is your tutorial, for example. Whatever you aim to solve, just name it real structure. Okay? This is the real structure. I show it with R. Okay? Whatever it is, if it is a beam, a frame, a truss, whatever it is, just name it. It is my real structure. And you will have a virtual structure as well, which is virtual, let's say, let's call it. What is the virtual structure? The virtual structure, I show it with V, stands for virtual. The virtual structure is exactly the same structure of your real structure without any loading. Just draw your structure without any loading. Forget about the loading in your real structure, without loading.
I'm not supposed to put one plane in.
Yes. The virtual loading is up to you. You can put whatever you want on your virtual structure. One example can be 1 kilometer, but you can put 2 kilometers, 3 kilometers, 4 kilometers, whatever you want. What direction, whatever you want. Doesn't matter. How many forces, 1 or 2, whatever you want. It's really up to you to put the force on your structure. How many up to you? What value for your force up to you? Which direction up to you? But it's beneficial for us to put the virtual force on virtual structure based on what we want to calculate as a deformation in our structure. How? Like this. This is the formulation of virtual work that we are going to use. Okay? It is really very similar to the formulation of Castigliano. Just to recall, this was in Castigliano, it was like this, M2 dx over EI, wasn't it? In Castigliano. We worked it with this formulation 3 weeks, I think. It was M2 dx over EI. In Castigliano, it was like this. In virtual work, the M2, the M squared, is like MV/MR. MV means M in virtual structure, MR means M in real structure. Right? It's easy to memorize it if you have memorized the Castigliano's theorem. So, the right-hand side is really easy to do because, first of all, we don't have any torsion. Forget about this. Torsion is for some particular 3D structures. For now, we can neglect the shear force because somebody told me, wait, don't calculate any shear force because we are going to do it in our coursework. I want to surprise you because we will do something fantastic in A7 of the course. And I trust all of you that you will figure out everything about the shear force deformation. So for now, we forget it. Also, we forget about the axial force. Because, for example, in beams, axial forces are not important. At least for now. Okay, when we go to some frame structures, axial forces are somehow maybe important. Really, the most important one is this integration. And calculation of this integration is really easy because, again, it says summation over all elements. MV comes from virtual structure. MR comes from real structure. Dx is the variation of integration. EI is a constant, right? The most important thing is to understand what is the left side of the equation. 1 times delta R. Delta R is what you're aiming to calculate. Means delta deformation, R means real. Delta in real structure. Deformation in real structure, right? What you want to calculate based on your tutorial, your example. For example, you're aiming at calculating this one, delta R, how this deforms, right? How the points B, for example, if it's BA, goes down. Delta R is the deformation of point B along vertical direction, right? If you're aiming to calculate delta R, you should go to your virtual structure, put a force on the same point you are aiming to calculate delta, means B. In the direction that you are calculating delta, means vertical. Put a force here along the deformation, and the value can be 1 or whatever you like. If you put 1, you should write 1 here. If you put 10 kilonewton, you should write 10 kilonewton. If you put 20, if you put 20 there, it's not always 1. 1 is because it's simple. One is good, we like one, because it multiplies with everything and it's still very helpful to say. Otherwise, we can put whatever you want. The left-hand side means the virtual work, the virtual force multiplied by real deformation. Here are some energy-based virtual internal bending moment times by virtual real bending moment. Okay? What we really do in practice is the right part of the equation is very easy to calculate. You just need to understand what is the left part and how you should put the virtual force on your structure. Okay? Let's do it in a real example. Any question in this slide? So let's proceed to this example. This is my structure. A column, a beam, a P here, A, B, C. Both elements have L as lengths and EI as constant. The question is find YC, means the deformation of point C along vertical axis. Only bending moment effects are important in this tutorial, right? We need a real structure, which is this one. This is the real structure, which is whatever you have in your tutorial. And the virtual structure. The virtual structure is the real structure without loading, and the loading on virtual structure depends on what you are going to calculate, right? I'm going to calculate YC in the vertical direction. That's why I put a virtual load here in the vertical direction, and I just put 1 as a value. For this one, the left-hand side of the equation will be the virtual load, which is 1, multiplied by YC, which is the deformation of the real structure. And the right-hand side, only for the moment, remember, it is this one. I'm writing this one. Okay? MDMR. So, MR means the internal bending moment in the real structure. I need to cut here once and cut here once. Make 2 sections, one for beam and one for column. I will do it here and here as well. So this is the section for this one, and this is the internal section for this one. All right? If you just make a section, you don't. For this one, really, again, you don't need to calculate the support reaction because it's kind of cantilever. You can make sections from right-hand side, and you don't really. But if you want to calculate the support reaction, it's fine. Just do it and use the left part of your structure. That's also fine. But I just made 2 sections, and I just made the same 2 sections in the virtual structure. And keep in your mind, whatever sections you do in your real system, you should do the same in the virtual structure because they are going to sit beside each other in the same integration. See, they are going to sit beside each other in the same integration. They should be in the same X value. So that's why whatever I do in the real structure, I do the same in the virtual. So when I come up with the integration, the summation means for whole structure, which means 2 sections should be covered, one for a beam, one for column. This is this is MR coming from this one, right? This is MV coming from this one. The integration, the x varies from 0 to L, right? The second one, minus PL, is this one, coming from real structure, and minus L is this one coming from virtual structure. Again, from 0 to L, which means for the column from 0 to L, right? Two integrations are covering the whole structure, including the beam and column. You don't have any unknown in the right-hand side of your equation. It's just an integration over x. E, L, E, I, these are just some constants, right? If you do that, you will come up with 4PL3 over 3EI. And that is the deformation of quantity C along vertical direction. What would happen? Any questions so far? It is easy, isn't it? What would happen if I put my virtual force as 2 kilonewton instead of 1 kilonewton? You should answer. It's your wonderful question today.
Value will just double.
Absolutely. What's happening to the final answer? Is it untouched or something will change? Remember that I haven't touched the tutorial definition. The tutorial definition is find delta C for this loading. I'm just changing the loading for virtual structure.
The final answer shouldn't change.
Should not change. If I change my virtual structure and the final answer changes, it's ridiculous. It means that there are plenty of answers for a question, a unique question. That's not possible. If you double the virtual work loading, what will happen is you need to write 2 here, right? But all of these will be doubled. This is minus 2L. This is minus 2x. All of the MV will be doubled as well. It means that these will be doubled and this is doubled. So the 2 goes out from the 2 sides of equation and still you will get the same answer. That's why it doesn't matter what to put there as loading for your virtual structure. You can put 1, 2, 3, 10, 20, whatever you want. That's why we usually put 1 because it's simple. Otherwise, you're free to do whatever you want. Right? This is called linear systems somehow, again, because when if you double the force, everything is doubled. Linear systems are like this. When you double the input, the output will be doubled. If you double the force, the internal bending moments are doubled. Right? Any question on this slide? We go to the next. The question is this one. This is the real structure. Really, it's this previous one. I just added another column here with a roller support here. Again, the structure is determinate, but we have 2 columns and 1 beam. And the aim is to calculate delta, which is deformation, HB means horizontal in the node B. So I want to know how much B goes in the right-hand side, the horizontal direction, okay? Only bending moment and axial forces are of interest. So axial forces means we are going to account for this integration as well. The shape of the integration is exactly like this. Just NV means axial force in virtual structure, NR means axial force in real structure. Okay? So we will have two integrations, one for bending and one for axial force. So this is my real structure, which is whatever I have in my tutorial with the force. And this is the virtual structure, which should be unloaded, nothing. The loading is up to me, up to you, whatever you want to put there. But we put a loading that helps us to use the equation of virtual work. So my aim is to calculate delta HB, which means the formation of B in the horizontal direction. That's why I put a unity force here in the horizontal direction at node B. Because I want to calculate delta at B, I'm going to put at B. Because I want to calculate the horizontal deformation, I put a horizontal force there, equal to 1. You can put 2. The value is really up to you. If you put 1 here, the left-hand side of your equation will be 1 times delta HB. The left-hand side always is the virtual force on your virtual structure multiplied by the formation in the real structure. To be honest, we have here some reactions as well. And to be honest, in the left-hand side of the virtual work should be the whole virtual forces times delta of real structure. Okay? But for the support reactions, they will be 0, because if I put, okay, this one times the real deformation of this point, horizontal direction, it's 0. Right? The next one times this is 0. This one times this is 0. Any load on your virtual structure should be multiplied by real deformation in the same point in the real structure. Just keep in your mind this one, because if you have some support settlements, you will see in the following examples, this would get important. In the left-hand side, you will need to change something, okay? So the left-hand side is really the summation of all virtual forces multiplied by real deformations. For now, I have only one, okay? So, because I have 3 elements, I really need 3 sections, don't I? I need to cut here, here, and here. 3 times 3 sections to cover whole structure of mine, right? This one is for this. This one is for this one. This one is for this section. It should be easy for you now to do that, because you need to write equilibrium equations to come up with the support reactions, then just cut the structure from X as a variable of X and just come up with the internal forces, right? This should be something that you really had several examples from the beginning of the thing. So For the virtual structure, we do the same sections. The virtual structure, for sectioning virtual structure, we just follow the real structure because, again, they are going to sit beside each other in the integration. So they really need to have the same X in real and virtual structure to be consistent when you write the integration. So whatever you have made in the real structure to make sections, you need to follow those for the virtual structure. So this one is really like this one is really like the second one, and this one is really like the third one, but in the virtual structure, right? And to be honest, you don't really need to think of these three sections in the virtual structure because the virtual structure is the same as the real structure with p equal to 1 in this case. So really, I don't need to bother myself for the section. This is really this section, just set p equal to 1. The second one is really this one, just p equal to 1, and the third one the same. If you set p equal to 1 in real structure, you will come up with a virtual structure. So when we come up with the different sections in the real structure and virtual structure, we can write the equation of virtual structure, virtual energy. As I said, the left-hand side is 1 times delta HB. 1 comes from the virtual, delta HB comes from the real. And the right-hand side, you will have 3 integrations for 3 sections, 3 integrations for the bending, and 3 integrations for the axial force, right? So one of the integration is 0 because m is 0. The third one is 0, so I really don't have anything for the third one. The first one and the second one are these. This is the first one for bending moment, and this is the second one for bending moment. The third one for the bending moment is 0, nothing, because the third section has m0, right? So for the bending moment, from the 3 integrations, we only have 2 of them. The third one is 0. For the axial force, the second one is 0. We have again 2 of them, right? For the axial force from the 3 integration, again we have 2 of them. The second one is 0 because nr and nv are 0. We have the first one and the third one, but they are somehow the same. P1 minus 1 minus p. When they sit together, the multiplication will be 1, 3. If 2 is because of that. We have 2 integrations identical. I just combined them and just put 2 there, but they are really 2 integrations. So we have really 3 integrations for bending moment and 3 integrations for axial forces, but one of each is 0. Okay, 2 and 2. When you combine 2 integrations for bending moment, you can recall them like this. Those integrations who have EI are corresponding to bending moment. The integration with EA is related to the axial force, right? So nothing is unknown in the right-hand side. Right-hand side is just integration, and you need just really to integrate some polynomials. So if you do the integration and combine the first 2, you will come up with this one. And for the integration of axial force, you will come up with 2PL over AE. This is exactly what you will have in your coursework. You will come up finally with some term with EI in it, which represents the bending moment, and some term which has AE, which represents the axial force contribution here. But in your coursework, you don't need axial force contribution, you need shear force contribution. Just the integrations are different. So, the problem is solved, and we know that this is parametric, but we know that this is the contribution of bending moment, and this is the contribution of axial force. But I cannot go further unless I have some numeric values for the parameters, okay? Just to have some sense about the results, I just assumed some values for the forces, lengths, and cross-section area, and modular of elasticity, whatever you need. And I just replaced them into the problem, into these two parts of the problem. And I came up with delta HB as 8 centimeter for the first term and 0.005 centimeter for the second term. Altogether will be 8.005 centimeters. You can imagine how important the contribution of axial force is. Right? How important is it? From engineering point of view, if you say, okay, the deflection of this floor is 8 centimeters. Somebody else says, no, the deflection of this floor is 8.005 centimeters. Which one makes better sense from engineering point of view? It's really 8 centimeters. It doesn't make sense, 8.5005 centimeters. What does it mean, that 0.05? It's nothing. That's why in majority of cases, we or the designer of the tutorial or example says, just eliminate the contribution of axial force or shear forces. Because in majority of cases, it's like this. The contribution of axial force into the deformation, axial force is there. Axial force is not zero, negligible. You cannot neglect axial force. Axial force is there, it should be there to satisfy the equilibrium equation. But the contribution of axial force into the deformation is negligible. Right? Because it's very different. If you make a section here from beam to column, this is B, the column, the axial force is like this, and I mean, if I cut like this, an epsilon from beam and column, and this is beam and column, the axial force is like this is like this is like this. These are the same thing. The axial force in the column is the shear in the beam, and vice versa. The axial force here is shear here, because of the 90-degree connection of the beam and column. You can never say axial force is negligible or shear force is negligible. If you neglect shear forces, you're affecting the equilibrium equation, that the equilibrium equation will not be satisfied. All the forces are there, but the contribution of some of them, which are usually axial force or shear force, into the deformation calculation is negligible. These are two different statements. So, this is always the case, not always, this is usually the case for the shear deformation calculations, as we have done for several cases. And for A7 part of your coursework, you're dealing with a problem designed to understand when and how, in some cases, it is not negligible. Okay? The A7 of your coursework is aimed to that. to see and understand why and how, where the contribution of shear forces are not negligible. You should account for them, right? Any question on this? Again, we come back to truss structures. Truss structures are really also important and also easier than frame structures because they just have axial forces in the elements, right? So before we start, I repeat the equation of virtual work again. Summation is for all the elements. And integration, we had in general 4 integrations. One for axial force, bending moment, shear force, and torsion. Torsion, neglect about torsion is for 3D. Neglect about shear forces and also moments, bending moments. Why? Because in truss structure, we don't have bending moment. We only have axial forces, don't we? NV, NR, dx over AE. For truss structure, we only have one of the integrations, which is the axial force integration. NR and V dx over AE. But before I proceed with the example, I want to bring this into light that in the truss structures, always the NV or NR are constant along the length of an element, aren't they? Because always in a truss structure, one element has either compression or tension forces inside it, and it's constant along the length. It doesn't vary, right? That's why these NV and NR can get out of the integration because they don't depend upon the X. They are constant in each element. So you can really say summation over all elements, NV, NR, and integration dx over EA, or AE, from 0 to L. They can get out of integration. And also AE can get out of integration because they are constant as well, right? The integration is really integration of dx from 0 to L. What is the result of integration dx from 0 to L? You tell me. NV and R integration from 0 to L dx summation over AE.
So not L.
Yeah, it is a integration. Dx is x. From 0 to L means L minus 0, L. Good. It's L. It's simplified to NV NR L over AE for all elements. For the truss structures, to be honest, you don't really need to deal with any integration. You need to only calculate this for all the elements and make a summation. Right? It's easier and it makes a space for us to do it more rapidly and more beautifully by making a table. And let's see how does it work. For example, for this one,
it says that determine the vertical displacement of C of the steel truss structure shown in figure below. The cross-section area is 300 square millimeter and module of elasticity is 200 gigapascal, right? The real structure is exactly what you have got in the definition of your example. This is the real structure. The structure is determinate. There is a support, two supports, a simple one and a roller one. And this is the real structure which is sold. This one is the real structure. There are two forces, 20 kilonewton. What you need to do is just to write the equilibrium equation to come up with these two support reactions, right? Then start node by node and go through all the nodes and write the equilibrium equations. For example, here, if you make a section from here, have two elements, and write the equilibrium equation for this part, you have two unknowns and a 20 kilonewton there. If you write summation of Fx and Fy equal to 0, you will come up with this force and this force, right? Then move to the other one, you will come up with this one and this one. Move to the other one, you have this, you have this, you have three, it's not good. Go from this way. You have this one and this one, go to this one, you will get these two. Okay? You move to the other one, you have this one, you will get this one and this one. Then you can move here, you have this one, you will get this one and this one. You just move node by node through the whole structure, writing equilibrium equation for each node, you will get all of the internal forces for the truss structure, right? The virtual structure, this is the virtual. The virtual structure is the same structure, but the loading is up to you to write whatever, to load whatever you want. What you load is depending on what you want to calculate. So it says that the vertical displacements of joint C, okay? So go to your virtual structure and put a vertical force on joint C equal to 1 or 2, whatever you want. So I go to the virtual structure, I put a vertical force in joint C along the vertical direction and equal to 1, right? And solve your virtual structure again against this one. How? Again like this. Come up, write equilibrium equation, come up with the support reaction, go node by node and find all of the internal forces. You have all the forces in the virtual and real structure, right? How many elements you have in general in your structure? Nine. I have 9 elements in my structure. 1, 2, 3, 4, 5, 6, 7, 8, 9. You can name them. These are 9 different elements. That's why I tell you it's better to make a table. You can do it without table, but it's more beautiful and organized with a table. You have 9 elements together to cover whole structure, because this summation means you need to cover whole the structure. You need to have all the elements into your formulation. So for each element, this is the virtual and this is the, this is the real. Each element has a force in the real structure and in the virtual structure, right? This column comes from these forces. This column comes from these forces, right? And this is the length of the element. That's from geometry. It's known. So what I'm going to do is to calculate this one for each element and make a summation for all elements. So this is really NVNRL. It's trying just to calculate the denominator. But you can do it at once with AE. It's okay, whatever, it depends on your taste. Just multiply these three together, you will come up with this. And if you make a summation, will be this. And just put it here, and AE is here. You're really trying to solve this. And you can really calculate this in your table and make a summation. It's probably really depends on you. And this is the left-hand side at V roads. And you've come up with delta C equal to 6.16 millimeter. Take a deep look and see if there is any part that you don't get clearly. If there is any part you have any doubts, just tell me.
What's the reason for the line in the room one? Is it
Which one?
intention? I know the actual courses.
These, you mean this one?
And actual, oh yeah, those ones.
Mine is they are in compression. But it depends on the loading you have. And when you go through the, for example, when you go through the, which element is it? E and FE. BE, and yeah, BE is good. For example, to BE. Okay. And it is, okay, in both cases, they are good. For example, here, okay? When you write equilibrium equation, you come up with these two at the fourth reaction, okay? You need to find the internal forces for different elements. You need to start from some nodes. I start with this node, which is node D, isn't it? So node D is like 20 kilonewton, and there are two forces. This is FDE, and this is FDC. Okay, the equilibrium equation should be satisfied with this small section I made. Okay, what is the equilibrium equation? It says summation fx should be 0, which means fx means okay, what is x? This is x, this is y. Okay, means minus FDC minus FDE if it's alpha, cosine alpha. Okay, summation Fy should be 0, which means 20 plus FDE sine alpha. If you solve these two together, you will come up with minus 28.3 for FDE. And what does it mean? It means that this is not in agreement with what I've put here. What I've put here is intention. Okay? It's intention because the rest of the element is here, and I should do like this. It is intention for the element. Okay? if you put this vice versa, you will get with a positive value. If you put it in compression, you will get it in positive value, but in the first place, we don't know which one is positive, which one is negative. That's why we put all the forces in tension, those will come up with the negative value are in compression. Right?
Yeah.
It's always the convention that we follow. We always put the internal forces in tension, those that will come up with negative values at the end, they are in compression. Anyway, you can stay with this and minus 28, or you can put like this in this direction and put it positive 28. Okay, but we don't do that really. We stick with minus 28 all the forces in compression, in tension. Any other question? If you put 2 kilonewton for the virtual structure, what happens? Instead of 1 kilonewton for the virtual structure, I put 2 kilonewton. What happens? All of the internal forces will be doubled. This column will be doubled. When you go here, this one will be doubled because all these terms have something from virtual which is doubled. And this one should be 2. So in the left-hand side, you will have 2. The right-hand side, you have the left-hand side is doubled, and the right-hand side is doubled. Nothing changes. The last point, but not the least, the final delta C, which has obtained equal to 6.16 millimeter, is positive. Sometimes that's negative. What does it mean if it's positive or negative? It means that when it's positive, it means that this delta C is in the same direction that the virtual force I put here. I was free to put, let me change the, I was free in the first place, I was free to put a force here like this. Okay? If I would put the force like this, all of the virtual column will be vice versa. It will be negative, 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 positive, 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 negative, positive, negative. If I change that, all of this column will change. And for that reason, you will come up with minus 6.16 millimeter at the end. It means that, if you do that, it means that the deformation, which is negative at the end, is in contradiction with what I have put in my virtual structure as a virtual force. So I put it in the top, it's not in the top, it's in the bottom direction, delta C. But because I don't know in advance, in many cases, not here. Here I know really. Somebody is standing on a bridge, so it should come down. But in some cases, it's not always the case that I figure out at the beginning that the deformation is coming down or up. In some complex structures, we cannot really guess in the first place. So it doesn't matter. It's okay. You're free to put your virtual force on your virtual structure in one direction, no matters, up or down. But you know, you're aiming to calculate vertical displacement. It should be vertical. It should be the y direction. But from top to bottom or bottom to top doesn't matter. Whatever you want. But whatever you get at the end for your deformation tells you what is the correct direction of the deformation. So if you put it from like the blue one, you will get negative, which means it's coming down, not up. But if you put like the red one, top to bottom, you will get a positive value at the end, which means you have done correctly at the first place. And it is from top to bottom. So the sign of the final value for the deformation speaks to you about which direction is really the correct direction of the deformation. Right? Any question? This one takes a little more time, and maybe it's better to leave it for the next week because it has some new things. And okay, we don't. If I start this one, probably will clash with the next one. As a conclusion, please try to recap with what we have taught so far from the beginning of the semester. But if you are behind the schedule and you want to just recover, please start with the Castigliano and virtual work then so you will get updated for the next lecture. First of all. Second of all, please go to the Moodle page and watch those two videos about ETABS and try to start your coursework, okay? You have 3 weeks until 25th of November to draft your ETABS model for the coursework, okay? And we will speak about it on 25th. This is our short program for the next 3 weeks. And for the next 3 weeks, we will finish virtual work. And when we finish virtual work, we will move to the matrix analysis, which is the initiation of the stiffness-based approaches rather than the force-based approaches. Good luck. See you next week.
Not into it.